So hemoglobin has iron in there as well, but it never flip-flops, it just stays as +3. And I'm not trying to say hemoglobin and cytochrome are similar, except for the iron part. Hemoglobins, I think they're much more complicated molecules, bigger molecules. When I say that, I'm not sure of that. All right, so our step 3, oxidative phosphorylation. It ties cellular respiration, right, the use of oxygen to create water, to making the actual ATP. And for every NADH, we get 3 ATP. And for every FADH2, we get 2. Now, this is going to be on the chart that you're given in the notes and that you're going to be allowed to use on your test. But sometimes students don't seem to recognize why I say it's true. I'm going to try to show you that once today, and I'll come back to it again as the stuff to make a little bit more sense. And if I'm getting writer's cramp, I'm getting clicker finger. So just maybe to review a little bit of this, if I give Hunter an electron, what's happened to him in terms of oxidation reduction? Got reduced. Yeah, so one way we might even designate something like that, we could say Hunter, and then put a little subscript, reduce. We take the electron away, now what is it? Yeah, it still looks pretty much the same, doesn't it? Yeah, the core of Hunter is still there. So we call this Hunter Ox. Yeah, or the Ox Hunter. Yeah. That's probably where the name came from. All right. So here's a chart that you guys have a little trouble understanding at first, especially. But remember I said we start with either NADH, or look down here we can also start in green FADH2. Those are starting points. One of them happens to start lower. If we think about energy, these things have higher energies as they go up. They're cycles. The NADH is going to get oxidized, and then the NAD plus gets reduced again. That's taking place somewhere else. I'm being very vague about this. That comes from us consuming sugar. A huge pathway that we're going to study later, the Krebs cycle and glycolysis. We'll see where the NADH and the FADH come from later. But if we just start with NADH, it gets oxidized and then reduced. But again, that's a go somewhere for this. That's somewhere else. Different part of the cell, generally, or the mitochondria. Cell, yes. And what happens is that as this gets oxidized, remember something else has to get reduced. This is getting oxidized. This arrow, you see these arrows are pointing the same way. Flavoprotein is getting reduced. So NADH is passing electrons and/or hydrogen ions onto the FG, flavoprotein. Flavoprotein gets reduced. And then flavoprotein can get oxidized back into flavoprotein, and it can reduce coenzyme Q. That one was mentioned specifically in that little video we watched because it produces hydrogen ions that flow through the membrane. Right, remember that hydrogen ion gradient they were talking about? This is one of the sources of hydrogen ions. So we've got a bucket brigade, so to speak. It goes on and on, right? All the way down to oxygen. It's the last step. As we go down, these are better and better electron acceptors. Oxygen is the best electron acceptor. Now, you are going to, things appear and disappear in these diagrams, I'm not really concerned with. I'm not always talking about hydrogen ions passing through, but there are electrons being passed through this whole system. I thought, I haven't really done this before, but I will try this. I only made the last 4.
I have a question. So is this process like a very slow, tedious process?
No,
or is
it's
this
a
like
very
a
rapid process.
like
It's
just
happening
like
continuously.
in a second?
Yes. And constantly. Constantly, many
But like-
cells over and over in the same cell.
Like how fast does it take
In
to get
mitochondria.
through? Is it kind of like the neurotransmitters where it's just so?
I think we do. I guess I don't really know that.
Okay.
Does anybody know that? You guys know baby biology at all? It's happening very rapidly, and it's happening constantly in every cell, every mitochondria, every cell. Some cells are packed with mitochondria. Yeah. All right, so, look, we're gonna start cytochrome B. Rachel cytochrome B. Okay? Nicholas is cytochrome C1, Aspen C, and Nico is cytochrome A. So if they're passing electrons, what happens when Rachel gains an electron, chemically speaking? It gets reduced. So, right, we could say, here's Rachel. Sneeze there, sorry. And she's going to get reduced by gaining an electron. So now we've got Rachel reduced. And here was Rachel oxidized. Pass your electron on to Nicholas. Okay, so Nicholas was oxidized. Is that right at all? Right. What,
Yes, yes, it is right.
is it right? Oh, okay. Well, he was oxidized, right? And then he's going to get reduced because that electron is passed on to him. Okay? So what's happening there is we wrote an equation for that. We could say,
That's cool.
wait a minute, is that right? I didn't see right.
It's a little upside down, the top one, I think.
Yeah, I'm sorry. That's not, yes.
Yeah.
Sorry about that. This would be the reduced form.
Yeah, and then
And now, there's where we started. We started with Rachel getting an electron somehow, me just giving it to her. Yeah. So Rachel, right, let's abbreviate this, rocks, gained an electron, right, to become, or red. Yeah, right, she gained an electron to become Rachel Red. Okay. But let's look at this one. Rachel Red then is going to react with Nicholas Knox. And what's going to happen? Rachel Red is going to become Rachel Ox, and Knox is going to become Red. Right? You see what I'm trying to show you? You can see these as chemical equations. Right? This is a reactant, that's a reactant, here's our product. Some of the arrows go the other direction, right? Our next set of arrows, Nicholas reduced, is going to go on and pass this electron on to Aspen, right? So then we have Aspen, Ox, becoming Aspen Red, right? And so we could write an equation for that as well. I mean, I want you guys to be able to write those equations. Some other aspects of this. Over here, I just put in some things about enzymes, just because I want to start emphasizing enzymes. So there's a lot of enzymes involved in this. The oxygen is coming from the breathing, the water, what we exhale. Over here are problems. Here are poisons. Rotenone is a powerful poison for at least certain things. Come from some kind of root down in Central and South America. You remember my beach fuzzy professor? He got in trouble with a lot of things. He made a lot of bad choices. Especially actually kills fish. And this is a pretty common way in places like South America and Central America to go fishing. You know, probably not legal, but you grind up the root that produces a rotenone, you throw it in the river, and the fish suffocate, and then they float to the surface, and right, it's a pretty easy way just to gather them up. This professor of mine had gotten a grant to study ways to collect fish. Right? If you're trying to find out what's in a river, I mean, how are you going to find that out? You go to the Columbia River, how do you find out what kind of fish are there? You go fish, right? Catch them, you. But you're probably going to be limited as to what to catch, and it's probably pretty time consuming. And you're probably going to miss a lot of things, right? A lot of little minnow type things that maybe can't bite that or don't eat the worm or whatever you're fishing with. So that's good for game fish. You can find out where you have bass there, there's trout there. But you're probably missing a lot of things. Little sculpins that live under the rocks, right? They're hard to find. They're hard to catch. So you can electroshock them. I did a lot of that. I electroshocked 14,000 fish that have been collected. Yeah, so you electroshock them and then you catch them in a net. And you can identify them, and then you get preserve them further back, or preserve most of ours. But you can take a net, right? You know, people you see in probably more third world country, right? They're catching fish with a net. They put a net out. Or you can track them on a net behind a boat if they're big enough body of water. So we do a lot of that too. We take nets out of seines and kick the rocks. We have people scaring the fish down to us, and then you look the nets up and see what you have. Well, none of those methods are completely effective, right? So he got a grant to study which of those methods were most effective. So this is a little bit before my time, but you know, he just had all these students out there electroshocking and kick nets and all kinds of other ways to collect fish, and figure out what they caught, right, and tabulate it. And then he had his grant to dump rotenone in the water to kill all the fish, and then they just had a giant net across the river, and then they could really see what was there. Does that make sense? And then they could evaluate the efficiency of these different methods. Well, this is a pretty big river, the New River in West Virginia, right about the size of the Willamette River, around Eugene at least. So it's a pretty big river. He made a mistake and forgot he could neutralize rotenone. He didn't do his calculations right. He didn't have enough to neutralize the rotenone, so he actually killed all the fish for about 3 miles.
Sorry guys, my bad.
So rotenone stops it. Rotenone stops this process. Anthomycin is a antibacterial, right? What's the word I'm looking for? Like penicillin. What do we call penicillin? Antibiotic, right? Yeah. So many poisons work. When we hear about poison, a lot of poisons work by disrupting the system. You know, I asked you, started it off asking you what kills us. Well, if you don't have oxygen, then there's nothing out here to collect the electrons, right? Somewhere past NICO, as these electrons get passed down, we've got to have something to take the electrons away. If I'm the oxygen, I take the electrons from hydrogen, I become water. Well, what if there is no oxygen? Poor Nico, he's stuck. He's stuck with that electron. And now he's already reduced. That means that Aspen can't reduce him, right? He has to be oxidized to get reduced. So now he gets stuck with electrons coming down the path. And all the way up, right, these electrons just back up and nothing happens anymore. Without oxygen, or without any of these steps, we take Aspen away, it's not going to work either, right? Or something, if some chemical like cyanide sticks to her, makes her not work, right, then we get bottomed up. So without something, it's not a push so much, right? We're not pushing electrons through. Oxygen is pulling electrons through. Without something in this chain, the electrons can't get passed all the way through, and then none of these things happen. Okay? So that's usually how poisons work. Now I want to show you something else here. Because other things happen, right? Here we're just focusing on the oxidation and reduction, but other things happen in certain steps. In this step, we get ATP. Right? That's another part of the equation. So NADH plus ADP and PI and oxidized flavor protein react together to make NAD plus, FPH2, and ATP. Right? These are the products, these are the reactants. Okay, you gotta realize, you gotta follow the arrows. Here's a reactant, product, and that's the equation. Okay? And then, as we're going here, right, reactant, You know, I said NADH makes 3 ATP. Oh, look, they're right on this chart. 1, 2, 3. There they are. Okay? FADH2, I said makes 2. Just wrote that down in your notes a few minutes ago. FADH2 skips this step. It starts here. So it has lower energy. And look, it's off 1 and 2 ATP. So they're in this chart. So you never have to memorize that. As long as you understand that. Yeah.
Are the reactants are just sort of floating around? Yes.
Yeah, they're in the cell.
Okay.
Yes. They're probably associated with enzymes. I'm not sure of that, but they're probably associated with enzymes. They are just.
So, but the NADH, okay, all of the like lipoproteins, the coenzymes, they're stuck in this membrane.
Yeah, they're stuck in the membrane.
They're stuck in there acting.
Yeah, these are
like
membranes, yes. And they have to be put in the right order.
Mhm.
Yes. There's one little video we'll probably watch at some point, where they try to relate this to a truck or cookies. Like if you bake cookies, you mix all the ingredients together, it doesn't matter where they end up, you got a cookie at the end. You mix up all the parts of a little truck, you don't necessarily get a truck, right? These have to be in the right order in the membrane, you know. So the spatial arrangement is important. Yeah, so they're not really floating around. They're in the end. Now, some of the other things, right? The ATP has to go somewhere and do something. The NADH has to come from somewhere. It's coming from another part of your cell. So those things are floating around. The hydrogens are going through the membrane. Okay? So we can write chemical equations. As I was showing you, right? Here's a segment of this. So since the arrows go this way, reactant, 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 product, product, product. Okay? So there's my equation for that, right? Here's my reactants. Here's my products.
Do you want us to draw a little like diagram to see?
No. Don't do that. No. In fact, you don't necessarily have to write it in here. They're going to ask you to try one on your own here in a minute. Watch these, a little bit different. You know, we can do it that way, where I say ox or red, as a little subscript. We can also, so we can say like cytochrome B oxidized or reduced. We can also do it with the iron, right? The iron, there's our oxidized form of iron, there's our reduced form of iron. But I like to do the ox or the red. So let's just try, we'll do this in a minute. So here's our overall picture so far. We're going to be filling this chart, learning a lot more about this. What's in purple is sort of what we looked at today. At least parts of it. Like we didn't count any numbers yet, for instance. But today we covered this section. So we're starting with either NADH or FADH2. They're going through the electron transport chain. From that we form water, we breathe in oxygen, and we get some ATP. Okay, that's what we've studied up till now. Where the NADH and the FADH2 come from, more, you know, what we're going to be studying soon, the Krebs cycle, glycolysis, these are big things on their own right. So it may look like one simple word, but there's 10 steps. Here there's another 10 or so steps involved. And there's this other weird piece that we break out and call it something separate, it's a little bit different. Doesn't have a good meaning. So we're going to fill in more parts of this as we go. This you can see is happening in the mitochondria for those organisms that have it, not all bacteria do not have a mitochondria, but these processes would still happen. Try just somewhere, I don't know, get a little spare space down there. Maybe just try, I was going to hand out a little green blue sheet of paper to make it work on your own more than anything, but see if you can turn this into a chemical equation.